tilde chart, right, then you can compare dx tilde 1 wedge wedge dx tilde n. What it's equal to is the determinant of partial x tilde j, partial xi, that matrix, dx1 wedge dxn. So this is the way in which differentials are related. If we were to compare the wedge product of the coordinate, the coordinate coframe, I guess we call it, between two different coordinate systems, they'd be related by multiplication by a determinant, like this. So, yeah. All right. Moving on here. Talk about the exterior derivative. What is the exterior derivative? Well, the exterior derivative is an extension of the differential that we learn in Calculus 3, essentially, to differentiate differential forms. And the reason it's called exterior is that the exterior derivative has the interesting property that if you take the exterior derivative of a p form, you get a p plus 1 form. So there are various ways to define the exterior derivative, right? The approach that Lee takes is actually quite ingenious. He basically defines the exterior derivative for differential forms in Rn, if I understand his argument correctly. Works out the properties of the exterior derivative on Rn, and then proceeds to argue that, okay, so you can basically you lift those properties up to the manifold using the pullback of the coordinate charts, because the coordinate charts go from the manifold down to Rn, where you already know how to exterior differentiate, kind of like we did last time, actually. In R3, we looked at the exterior derivative in R3 specifically. So those patterns can be proved for general Rn. In terms of explicit formulas, in terms of determinants and such. And anyway, so you can pull back the exterior derivative on Rn up to the manifold, and then he proves that I think if you had any other operation that had the properties of the exterior derivative, it would have to be that same thing he pulled back. Something like that's his argument. So it's a very cool argument. There is other ways to define it. The other way to define it is just to say that there's a unique operator D that satisfies its properties. So if you can prove the uniqueness of that, that gives you a definition. The other way, this is the way it was done in my course, is just to define the formula for the exterior derivative in a particular coordinate system, and then show that if you were to change coordinates, you'd still have the same definition. That is a third way to prove the formulation of the exterior derivative. So I'm not going to quite follow John Lee's book here. I'm going to go straight to the properties of the exterior derivative. So this is proposition 14.23, and I'm going to basically I think I'm going to more or less follow the approach that I had in my class, because I'll be able to show you guys an interesting calculation that I think you'll appreciate. The exterior derivative is linear over R. B, if you have omega, smooth K form, and eta, smooth L form on U a subset. Now he does it for, this is what I'm just talking about. It's all in Rn, okay? Then you have D of the wedge product of omega and eta is d omega wedge eta plus minus 1 to the KL omega wedge d eta. And C, if you take D and compose it with itself, you get 0. And part D, the pullback of d omega is D of the pullback of omega. So here we have F U to V a smooth map. All right, and he proves this through pretty much just explicit. He proves these properties by explicit calculation on the wedge product of the differentials of Cartesian coordinates, and it all stems from the product rule for the regular partial derivative on Rn, and the fact that partial derivatives commute for smooth functions. So like partial x, partial y is partial y, partial x. Those two things give you all of this. And then basically his argument is, okay, so if this is true, then you can just pull this exterior derivative up to the, to the manifold essentially, and define. So like here's how he would conceptually think of it. If I've got a differential form alpha up here, right, on the manifold, and suppose that I want to think about the coordinate. I want to think about it in subset, like a coordinate chart U, right? Well, then that gives me down here x of U, right, by the coordinate chart x. I can tell you what, I'll use phi for a second. He always uses phi. So phi, there you go. Feel better. So his coordinate chart phi, and so, well, how do I, oh man, wait a minute. That's the wrong way, isn't it? So if he's going to, how is he going to get it down to here? I guess you got to do the inverse of phi, huh? So phi inverse goes like this, right? So if I do phi inverse, pull back alpha, then that, that would be an element of like the K forms on, Rn down here, right? And then I can define, I can exterior differentiate down there all I like according to proposition 4.23. I can do everything down there like that, And so this is defined down in Rn, right? Anyway, I'm sorry, I don't want to, I'm not sure I'm accomplishing anything at the moment. So really, I'm trying to talk about theorem 14.24, where this is the existence and uniqueness of exterior differentiation, and it's the same properties that he just wrote for proposition 14.23, with the exception of property 4, which is that for the zero forms on the manifold, the exterior derivative is the differential. And so, here it is. So this would be an element of lambda k plus 1 on Rn, right? So how would I define, if I'm doing this, how would I define d alpha? Would be what? So this is down here somewhere, right? How do I bring it back up here? Pull it back, right? Pull it back with the coordinate chart. So then I do the pull back under the coordinate chart. of this thing, of the differential of the pullback under the inverse of alpha. So this actually is the definition, or it's a potential definition for the exterior derivative on the manifold if you want to take exterior differentiation on Rn as primary. And if you look at equation 14.22 in his proof for theorem 14.24, it's exactly what I just wrote down. However, he uses omega instead of alpha, but it's the same animal. And then he argues that it's well defined and that basically it has to have all the properties, all the same properties as this. And then he extends it to the whole manifold using the bump function thing as usual. There's a very hand-wavy explanation for what's done. All right, but after everything's said and done, what you have is this. The exterior derivative of the, let's use the same formulation that I had over there. So like for alpha in the K form over the manifold, the exterior derivative of alpha, all right, is equal to, it's just so simple really. It's the same thing I told you last time, Preston, which is that you exterior differentiate the component functions and you wedge with everything else that's already there. But the multi-index notation makes it seem so much simpler, right? Like if I expand on what am I actually saying here? What am I actually saying here? I'm saying that the sum over, let's say, J and then I1 all the way out through, what do you guys want to make alpha an element of what? Omega what? What did we do over there? We did a K form. So K it is. K form on M, right? So I1 through IK, that's how many indices I've got here. So what is what is this? I mean, if you like, I guess I could put the J last. Let me put the J last. I equals 1, 1 through K. And then I've got the sum J over J, right? I've got partial alpha I1, IK, partial XJ, dxj, wedge, dxi1, dxik. That's what it is. But it's very simple, really. You're just taking the differential of the component functions and wedging it with what's already there, right? So let us, if you don't mind, let us set aside this development, this wonderful, beautiful, logical development in Lee for a second, and take this as the definition, because this is an actual competitive, I mean, this is a competitor for being the definition. This formula could serve as the definition suitably understood. And let us prove B. Because I think if you can do that calculation, you understand a lot. And at least I myself really, really enjoyed that calculation when I was a student and I understood it. I felt like I'd really learned something. Just because the notation, I mean, like, the notation is so foreboding at times here when you first see it. I don't know, I have this kind of mixture of horror and awe at times with the indices stuff, you know? So here, let's take the exterior derivative of this, right? D of omega wedge eta. All right, so we have, we have to figure out what is omega wedge eta, right? All right, so let me do that. So I probably should just figure out what's the formula for omega wedge eta to start with. Let's do that. Omega wedge eta. So we could do sum over I of omega I dxi wedged with the sum over j of, eta j, right? dxj. Then using the bilinearity of the wedge, pull the sum out, you know? So we've got like a sum over I and j of omega I eta j dxi wedge dxj. There you go. That's a good enough formula for it. Although, to be fussy, well, I'm a little worried about what I'm about to do. Well, I guess I'm just going to trust in the notation. Oh man, I better. Okay, so then, I believe then, this is the best I'm going to be able to do for today. Omega wedge eta is going to be what? It's like the sum over I and j, and then I've got what? Let's say like the sum over, let's say k, of partial omega I eta j, right? Partial xk dxk wedge dxi wedge dxj. So I'm working on kind of I'm keeping my multi-indices to avoid a lot of writing here. Okay, so then what? Well, we've got the sum over I and j, and might as well throw k into it. And then what goes on here? Well, I've got partial omega I, partial xk, right? Eta j. Oops, my j just went upstairs. I don't know what happened there. Is it sharp? Yeah. No. No musical morphisms today. Eta I, wedge eta j. And then, oh man, I'm sorry. Plus omega I, partial eta j, partial xk. All right, so I was trying to just do the product rule, right? The product rule. And we'll be done here in about 3 minutes if I do my thing right. So then, do you understand what happened here? So for like an arbitrary pair of multi-indices I and j, the product of omega I and eta j, it's just a function on the manifold, right? So by the product rule, you guys proved back in homework 1 for the coordinate derivation, right? We can do that. And then what you do is undo it. So like bring the k over to there, right? So you got, like, look at what you got. You got like a sum over I and j, a sum over k of partial omega I, partial xk dxk, all of that times your eta j, my bad, there was a wedge dxi, parentheses, wedged with eta j, dxj. So what I did, guys, is I just pulled the, nothing much really. I pulled this differential past the eta. We're allowed to do that because this is just a function. It doesn't cost you anything. It's just, you can move the function, past the dxk without any cost there. On the other hand, the other one, not so much. See, this guy, I have the sum over I omega I dxi wedged with the sum over j and k of partial eta j partial xk dxk wedge dx j. I made it. But think about that. What did I just do in order to write that down? See, think about the second term here, right? Think about why didn't I use all of that board space? I've got no good answers to that. But if you look here, see this dxk, see this dxi. What had to happen? I had to move this guy all the way through that. But remember what that is. You're talking about dxk wedged with dxi1, dxi2, dxi. How? Goodness gracious. K of them, right? K? How many were there? Did we ever say? We never said. Rats. Let's make this a P form. Let's make that a Q form. A P form and a Q form. Because apparently I'm using K as an index of summation now, and I probably don't want to make that the same letter. All right, so so you see I had to move this K past these differentials, and so it costs me 1, 2, P of them, right? Since omega is a P form. So I have to put a, right there, I owe you guys a -1 to the P factor. Huh. Oh? Oh. Dudes. Well, but I think what I have left over here is the differential. So if you look at it, so these sums you can just bring in, take basically, there's no j dependence here, so you can just leave this as a sum over I and bring the sum over j over here like so. So what you're looking at is d omega wedge eta plus -1 to the P omega wedge d eta, which means I've copied the answer from the book wrong, I think, because I like that answer. Oh, what do you know? KL, nonsense. This is not KL. What belongs here? Not KL. Just K. Just K. And we calculated it. Of course, my K is P here, but
That's okay.
that's okay. I like that. I'll allow it. Anyway, so there you go. That's differential forms in a nutshell. And I think once you guys work a few homework problems on them, it'll make more sense. There's some other formulas in terms of there's a really, proposition 14.32, it gives you an invariant formula for the exterior derivative. That is yet another way to define it. All right, so we should probably talk a minute or two about some of the other things I've skipped today, but I think that's good for today, and hopefully we'll be able to more or less stay on track going forward. Of course, you guys got a test next time, so you get questions about that, or we'll do that after the video.
Rip Jeff.